Hello, I would like to talk about our latest publication on hacking a quantum crypto system using the aftergate attack. We find this hacking particularly interesting because quantum crypto systems promise a new level of security in communication. Let's say that two parties, Alice and Bob, want to communicate. Then, in contrast to classical cryptography, quantum cryptography offers them a method with unconditional security, in principle. An adversary, Eve, cannot eavesdrop on the communication of Alice and Bob because she will introduce errors and is therefore detected. A security proof for such a scenario requires certain model assumptions for the devices of Alice and Bob. This works fine in theory, but what about in practice? In the next minutes, we'll ask the question, can real Alice and Bob communicate securely? And we'll show you that real device properties should be taken into account in the security proof, otherwise we'll get security problems. These are the physical crypto devices that are bread and butter for us, quantum hackers, but are obviously not possible to be shown in the publications. The crypto system we hacked is called Clavis 2, made and sold by Idecontic. On the left side you see the Alice module, on the right side you see the Bob module, and they're exchanging secret keys. This is how the Alice module looks from the inside. The bit sequence in QKD needs to be random, so here you see two quantum random number generator modules that perform this task. Next to various optical and electronic components you see the phase modulator that encodes the bit information on optical signals. These optical signals are sent by Alice. The optical fiber acts as a transmission channel. In a practical application, this is of course much longer and can be on the order of 50 kilometers. Here the optical fiber enters Bob. Bob also has a phase modulator to perform the basis choice. The two detectors in Bob are avalanche photodiodes working in gated mode. Here we see also some additions made by us so as to get some information about various electronic signals in the module. In a real attack, the adversary of course cannot access such information. However, it enables us to verify that our attack really works. The outputs from these electronic tabs are now observed on the oscilloscope. What you see are the gate pulses applied to the two detectors. This tells us when the detectors in Bob are active. What we also see is that Alice and Bob communicate in frames of about 1,000 pulses. We now zoom into a single frame and see individual gates. The system normally expects the quantum signals to arrive within these detection gates. Our attack, which is an intercept and resend kind of an attack, times the pulses, however, to arrive after the gate. We have checked various time delays and the intensity of the pulses to optimize the attack. To explain the principle of the attack, we need some theory. Here you can see an IV diagram of the APD, in which we can explain the Geiger mode of an APD-based single-photon detector. Before the gate, you see that there is a bias voltage applied to the APD, see the blue point. During the gate, the voltage is increased above the so-called breakdown voltage, see the green point. If your photon impinges on the APD, then an avalanche effect generates a large current. This generates the detection event. But what happens if we illuminate the APD after the gate? With a bias voltage below the breakdown voltage, the APD is in a linear mode. This means that current through the APD is proportional to the optical power. The APD merely registers whenever the power is relatively strong. The detector therefore has properties which are very much unlike the ones during the gate and also unlike the ones assumed in the security proof. In our publication, we show how to exploit this deviation. We simulate an attack of Eve in which she measures all quantum signals and resends bright pulses timed after Bob's gates. We found that the attack renders the quantum crypto system insecure for a large parameter range. So, we're in contact with the manufacturer Idecontic and believe that our work is vital for the practical security of QKD. Our team currently works on other attack on the Clavis 2 device, so we'll be back.